All right, Chemistry 1411. Let's take a look at question 30. Indicate whether the following aqueous solutions are acidic, basic, or neutral. They've given us the Ka for acetic acid. They've given us the Ka for hydrocyanic acid. And they've given us the Kb for ammonia. So the first one is ammonium acetate. So in A, we have ammonium acetate. So ammonium acetate is an ionic compound. And so when you put it in water, remember we're in aqueous solutions here, it's going to break apart to give you an ammonium ion, which is aqueous, and an acetate ion, which is also aqueous, right? And it's going to dissociate completely. So we're going to get 100% dissociation. So in our solution, we're going to have ammonium ions and we're going to have acetate ions. Now, will these affect the pH of the solution? The answer is yes. Ammonium is the conjugate acid of ammonia. And so it's going to be acidic. And so that's going to affect the pH. And then the acetate ion is the conjugate base of acetic acid, which is a weak acid. And so since these are both the conjugates of a weak base and a weak acid respectively, they will affect the pH of the solution. And so what we need to do is we need to find um, the Ka. We need the Ka of the ammonium ion because it's an acid, and we need the Kb of the acetate ion because it's a base, right? Again, acidic, okay? And the acetate ion is going to be basic. And so they haven't given us the Ka of the ammonium ion, but they gave us the Kb of ammonia. And so we can calculate the Ka of ammonium from the Kb of ammonia. And so we know that Kw, oops, just let that save. Come on, you. So we know that Kw is equal to Ka times Kb. And so for the Ka of the ammonium ion, we're going to say Ka is going to be equal to Kw divided by Kb. So we have 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And when we punch that in our calculator, we end up with 5.6 times 10 to the negative 10. So 5.6 times 10 to the negative 10. And so that is the Ka for our ammonium ion. So now we're going to do the same kind of operation for the Kb of our acetate ion because they've only given us the Ka of acetic acid. We want the Kb, so that's the conjugate base. So we're going to say here Kb is equal to Kw over Ka. You can probably see where this is going. We have 1.0 times 10 to the negative 14. And you notice that the Ka has the same magnitude as the Ka of acetic acid has the same magnitude as the Kb for ammonia. So divided by 1.8 times 10 to the negative 5, and of course we get 5.6 times 10 to the negative 10. And again, that is the, oops, where's my green highlighter? That is the Kb value for our acetate ion. And so since the Ka and the Kb are equal to each other, one doesn't outweigh the other. And so we're going to end up with a neutral. We're going to end up with a neutral solution in this case. Okay, so now in B, we're going to look at ammonium cyanide. So ammonium cyanide is also an aqueous compound. It's going to break apart to give us an ammonium ion. Okay, plus cyanide. So I'm going to move a little faster this time. So the ammonium ion is acidic and the cyanide ion is basic, like that. So what we need to do is we need to compare the Ka of the ammonium ion with the Kb of the cyanide ion. Whichever one is larger in magnitude is going to dictate whether the solution will be acidic or basic. We already worked out the Ka for the ammonium ion in the previous question, and we found that it was 5.6 times 10 to the negative 10. So they haven't given us the Kb of the cyanide ion, but they did give us the Ka of the hydrocyanic acid. And so we're going to say our Kb for our cyanide ion is going to be equal to Kw divided by Ka. So we have 1.0 times 10 to the negative 14 divided by 6.2 times 10 to the negative 10. And when we do that, we end up with 1.6 times 10 to the negative 5, like that. And so we can see that our KB is greater than our KA. Again, this is our KB value, which is greater than our KA value here. And so since KB is greater than KA, we're going to say here, therefore, solution will be basic. All right, I also asked you to go over this problem here. What's the pH when 100 mils of 1 molar HCl is mixed with 200 mils of 1.5 molar sodium hydroxide? And so this is going to be a neutralization of a strong acid, HCl, with a strong base, sodium hydroxide. And we should be able to write out that neutralization reaction. So it's going to look like this. We have HCl, which is aqueous. You mix that up with some some sodium hydroxide, which is aqueous, and we end up with a salt plus water. The salt is going to be sodium chloride, okay? And we're going to also end up with water. Now we know that sodium chloride is not going to affect the pH of a solution, and water certainly won't affect the pH of a solution. But we don't have an equal molar amount of HCl and sodium hydroxide, do we? So if we start with determining the number of moles of HCl, so I'll put N of HCl, so that's going to be equal to 1.0 moles per liter, our concentration multiplied by 0.100 liters. I'm just converting the 100 mils into liters, and we end up with 0.10 moles of HCl. If we do the same thing with our sodium hydroxide, we end up with 1.5 moles per liter multiplied by 0.0200 liters, and that gives us 0.30 moles. So you can see that we have more sodium hydroxide than we do hydrochloric acid. So now what we're going to do is we're just going to take that same equation that we started out with, okay, and we're going to make a quick ice table. So I'm going to say here HCl, a lot of handwriting here, plus my sodium hydroxide, okay, gives me my salt. Writing things down never hurt anybody. Plus H2O liquid. There we go. So we're going to have initial change in equilibrium. So our initial number of moles of our HCl is going to be 0.10 moles. The initial number of moles of our sodium hydroxide is 0.30. The sodium chloride in the water, we don't even worry about those, but we can see that the ratio of HCl to sodium hydroxide is 1:1. So we're going to consume all of the HCl, so there'll be none of that left over. But we're only going to consume zero point 0.1 moles of the sodium hydroxide, so we're going to have 0.20 moles left over. Of course, we're going to gain 0.10 moles of the sodium chloride. But again, we're not worried about that because it doesn't affect pH, but I'll just still write it down here. Okay, so now we know that we have the only thing that's going to affect our pH is going to be the sodium hydroxide, and we have 0.20 moles of our sodium hydroxide. So now what I'm going to do is I'm going to erase all of this, and I'm going to make a new ice table for the dissociation of the only species that's going to affect the pH of the solution, which is the sodium hydroxide. Okay, so let's make a new ice table for our sodium hydroxide. So sodium hydroxide is 100% ionic. It's going to break apart to give us sodium ions plus hydroxide ions, like that. I should have written AQ here. So we have initial change equilibrium. So I have 0.20 moles here, 0. All of this is going to dissociate, so I'll be left over with nothing. We're going to gain 0.20 moles here. We're going to gain 0.20 moles here. Of course, sodium isn't going to affect the pH, is it? Right? Sodium has no effect, but hydroxide certainly does, doesn't it? So there we go. So all we're left over with our 0.20 moles of hydroxide. And I'm sure many of you went from here to here directly. That's totally fine. But we want to calculate the pH of our solution. And of course, we can use the POH formula. POH is equal to the negative log of the concentration of hydroxide. but we need to figure out the concentration of our hydroxide. And so the concentration of our hydroxide is going to be equal to moles per liter, right? So we have 0.20, I can do better, 0.20 moles divided by our total volume. Well, what's our total volume? Our total volume is 100 plus 200. So that's 300 milliliters or 0.300 liters, like that. So when we take 2 over 3, we end up with 0.67 molar. So that's the concentration of our hydroxide. So our POH is going to be equal to the negative log of 0.67. And that gives us 0.18. So if we subtract that from 14, so if we take pH is going to be equal to 14 minus POH, we get 14 minus 0.18. So we get our pH is equal to 13.82, like that. And so there's our final answer. Our pH is 13.82.